So, good morning, all. I welcome the participants to the session on characterization of biomass for use in heat and power generation. Before going to the session, let me introduce our guest speaker, Dr. Lawrence. Dr. Lawrence has obtained his PG degree in chemistry from St. Joseph College, Trichy in 1980 and postgraduate diploma in business administration in Bharat Heavy University and obtained his PhD degree in chemistry from NIT-Trichy. He has joined in BHEL Tiruchirappalli in 1981 and acquired experience in the fields of water chemistry, chemical cleaning of boilers, and tube failure investigation. He has specialized in understanding the fuel-related issues using advanced fuel characterization techniques for power plants. He has carried out many research projects in power plant chemistry area and BHEL slag index developed by him for the prediction of slagging potential of coal during combustion. Now it's being cited by many researchers worldwide. After BHEL service, currently he is working as a freelancer power plant chemistry consultant, sharing knowledge and providing technical solutions to power projects. Dr. Lawrence has published and presented more than 35 technical papers in various international and national journals, conferences, and symposiums. He has peer-reviewed many technical papers for Elsevier and American Chemical Society publications. He is a member of the BIS Committee for Water Quality for Industrial Purposes, and he has a credit of 11 patents and 2 copyrights in the field of water chemistry, chemical cleaning of boilers, and fuel characterization. I welcome you, sir. Over to Dr. Lawrence.
So today's session will be dealing with the characterization of biomass fuels for heat and power generation. This is my topic of interest in 1990s. After that, we switched over to completely coal for BHEL. Lot of research work on coal side. This is topic of my interest in 1990s, biomass fuel. So let us have the overview. The world biomass production is 120 billion tons per annum. So much potential is available. 14% of world energy supply in rural areas through only biomass. But over the years, there's a decline in biomass utilization due to use of fossil fuels. We have a lot of coal and oil. So utilization becomes fossil fuels utilization enormous becomes so biomass utilization becomes reduced. Because of fossil fuels utilization, the emission level also has gone up. So biomass also now people started considering this opportunity fuel in the form of stored solar energy. Don't think biomass is a very much equivalent to coal. That's what I done a lot of work on that. 1 kg of pelletized biomass equivalent to a big grade of coal of Indian coal, 3,800 kilocalories per kg. Imagine. So biomass can be environmentally friendly and it can also be renewable resources because plants that can make biomass can be grown more and again. So biomass fuels provide substantial benefits as far as environment is concerned. The biomass combustion tends to generate dust that stays airborne longer than coal. This is what the picture you are seeing in the Punjab, Haryana side. Trouble burning of the cast, smog, and poor air quality. Not only that, it affects the capital Delhi very much. You can see that. See, last September, you will see the newspaper. The Indian government has asked thermal power plants located within 300 kilometers of capital Delhi to co-fire biomass with coal to reduce. You know Delhi, what is happening in the Delhi in the month of say November, December, January. Pollution, mainly particulate matter, aerosols, all because of the farming, the burning of straw fuel in and around Delhi areas. The Commission for Air Quality Improvement for the National Capital Region, NCR region, and the adjoining areas has identified 11 power plants to co-fire 5% to 10% biomass with coal. This is the direction given to all the 11 power plants, coal-fired power plants, to use 5% to 10% biomass with coal to cut pollution and to reduce dust stubble burning in farms, according to the Federal Environmental Ministry. Paddy straw banning It's a matter of grave concern in the national capital region and adjoining areas. Proper utilization of paddy straw is an important strategy among the various means to reduce the burning and that's one the. So there is a need availability in surplus biomass available in surplus. There is a need for disposal of agriculture residues. Not only disposal, present condition is safe disposal of agriculture waste. You cannot fire as you like in the farms. Non-biomass fuels again is renewable. It will give you neutral greenhouse effect. Say from photosynthesis that will be forming the biomass. From biomass we burn combustion mode. Again we are getting energy back to CO2. So this is what neutral greenhouse effect. Again biomass can be a source of liquid fuel. You can go for biodiesel. Last session you have seen the wood gas. Most biomass uses as a solid fuel. It's most used, though it's all very limited concern biodiesel, biogas. Most common is used as a solid fuel. There are opportunity. Industrial biomass can be grown from numerous types of plants, including miscanthus, switchgrass, corn, willow, sugarcane, bamboo. So opportunities are available to grow energy crops. Now, all biomass fuels are not same. There are a lot of variation within the biomass, various types of biomass. Same biomass in our country, in another country, there will be a difference in quality. So all biomass fuels are not at all same. That you have to understand. So to use the biomass for fuel or design a boiler or equipment for heat and power generation, one needs to understand the characteristics of the biomass in order to avoid possible problems and utilize the biomass more effectively. So there comes the characterization of biomass fuel. As I told you, in the 1990s, I have done a research project on these biomass fuels. There I have utilized all these 12 characterization techniques for the biomass characterization. Now I am going to explain whatever I have done in 1995. I have selected few biomass fuels for my research project. These are the various characterization techniques I have adopted. One is proximate analysis, other one is ultimate analysis. The proximate analysis is nothing but measurement of moisture content, volatile matter, fixed carbon ash. That's called proximate analysis. Then ultimate analysis, determination of how much carbon, hydrogen, nitrogen, sulfur in the fuel. Then calorific value, heat content of the fuel. These are all very important information we require for characterizing the biomass fuel or utilization of biomass fuel. Then chemical composition of the raw fuels. What are the ligno components or lignocellulose components available in the biomass fuels? Then flammability index of the fuels. Ease with which you can get a flame. Temperature at which you can get a easily flame. That is a flammability index of the fuel. Then thermogravimetric analysis of the fuel. Here what we are conducting the reactivity of or combustion rate of any fuel. That's called thermogravimetric analysis. Then differential scanning calorimetry. The earlier one is thermogravimetric. We are measuring a weight business, mass gravimetry. The scanning calorimetry leads to how the heat flow, how the heat is liberated from the fuels, what rate. That you can study the differential scanning calorimetry. Then char, thermogravimetric analysis, the char will be dealing. Then scanning electron microscopy analysis of the char particles. Then chemical composition of the ash. The earlier one, fourth one, chemical composition of the raw fuels. Here, chemical composition of the ash. How much is silica, how much iron oxide, alumina, calcium, sodium, potassium. Those things, chemical composition of the ash. Then melting characteristics of the ash, that is ash fusion temperature. Then chemical fractionation technique. So these are the 12 characterization techniques we will be dealing in this session. As I said, I have selected these 7 biomass fields my characterization study. Of course, people have done my focus is on these 7 biomass fields. One is coir waste, then groundnut shell, then bagasse, then sawdust, wheat straw, rice straw, and rice. These are the 7 biomass fields I have focused in my research project. Start with proximate analysis. I don't know how many are familiar with proximate analysis. So proximate analysis means determination of moisture content, volatile matter, fixed carbon, and ash. How we are doing simple terms, I will explain. You take about 1 gram of sample, it's weighed and in a crucible. The crucible is placed inside the electric hot air oven, maintained 105 to 110 degrees C, allowed to remain for 1 hour. Then you take it out, find the weight loss. Whatever weight loss you are getting at 105 to 130, keeping it 1 hour, that loss you can account for moisture. The percentage moisture is equal to loss in weight divided by weight of the sample. So this will give the moisture. The second one is volatile matter. The dried sample left in crucible 1 is covered with a lid and placed in the electrical furnace, muffle furnace, maintained at 900 degree. 900, some people say 925 degree. This is volatile matter. ASTM says 900, some people 925 degree. 900 degree. Keep it inside the furnace for 7 minutes. The sample should be covered and with a lid. Then take it out, find out the weight loss. So whatever weight loss for 7 minutes at 900 degrees centigrade is a volatile matter. So loss in weight due to removal of the volatile matter divided by sample by 100 will give you volatile matter content. So moisture, volatile matter. Then third one is ash content. The residual in the crucible 2 is then heated in the muffled furnace in an open condition without lid at 500 degree for half an hour. I will explain why 500 degree. That's the important point in 500 degree. Normally in coal and all, for ashing we will be doing 800 degree. For biomass specifically, you have to do at 500 degree. The reason subsequently I will explain. So ashing temperature for biomass ashes are 500 degree for half an hour. Entire become ash, then cool first in air and then in a desiccated way. Heating and cooling way may be repeated till the constant fry. So find out the percentage of residue, that is ash. So weight of the ash 100 divided by sample, take this give you ash content. So fixed carbon, one of the constants for proximal analysis, percentage fixed carbon 100 minus percentage of moisture, volatile matter as given. So these are the way proximate analysis being carried out. Moisture, volatile matter, ash content, and fixed carbon. It's a proximate analysis. The importance of proximate analysis is provides a valuable information with respect to the quality of the fuel. So for any fuel, proximate and calorific values are very, very primary analysis, very, very important analysis to understand the fuel. So from this, from moisture lowers the effectiveness calorific value. It quenches the fire in the furnace, hence lesser the moisture, better the fuel. Similarly, handling, higher the moisture, handling will be very difficult. Volatile matter. High volatile matter containing biomass burns in a very long flame, high smoke. The ignition point of view, flame stability point of view, volatile matter is good. So high volatile matter content means the high proportion of fuel that will be distilled and burnt as a gas and vapor. Volatile matter present in the biomass may become. So though it contains volatile matter, this same volatile matter may not be combustible completely. Sometimes methane may be there, hydrocarbon or CO2 may be there, nitrogen may be there, or water may be there. So don't imagine volatile matter completely useful. Part of the things may be combustible, part of them may be non-combustible also as a part of volatile matter. Ash is a use as a non-combustible matter which reduces the calorific value of the biomass. Moreover, ash causes hindrance to the flow of air and heat, thereby lowering the temperature. It often causes trouble during the firing by forming a clinker which blocks the interspaces of the grade-fired boilers. So ash will get a lot of problems, slagging, fouling, deposition, corrosion. Lot of problems will be facing with ash-related issues. We'll be dealing finally. What are the ash-related issues, problems? Then fixed carbon, higher the amount of fixed carbon, greater the calorific equilibrium, better the fuel quality. So these are the very. So basic input is your primary proximate analysis. See here, you see, if I told you the 7 biomass fuel, I have given the proximate analysis. The last one within the red is for comparison, I have given the coal analysis. So coir waste, groundnut shell, bagasse, sawdust, wheat straw, you can see the moisture content on dry basis, air dry basis, it varies around 7 to 10%. 7.8, 8.69, 7.94, 9. Mostly below 10% moisture content on air dry basis. All the 7 biomass fuels. Compare coal are similar to 5.47 on air dry basis. So if you compare the volatile matter, almost 3 times than that of coal. Coal, you have 23.6% volatile matter, whereas on all the biomass fields, 7 biomass study were 67, 66, 72, 69, 68, almost 3 times. So 3 times value of the coal, we have the volatile matter content in the biomass field. Highly volatile. Then ash content, it varies from 2% to around 14% or 15%. Only straw fuels, rice straw, we have 14.5%, and rice gas 14.9%. Then wheat straw 7%. All other things are say 2%. We have 3%, less than 2%. With respect to ash content, very much better fuel compared to coal. Coal, we have 39% ash content, average Singareni coal, 39%. Whereas biomass ash are right from you have 1% to maximum 14-15%. Fixed carbon more or less same, 22%, 19, 16. Coal we have 31%. So this with respect to proximate analysis of biomass fuels. So the overall overview, the moisture content vary within narrow range of 7 to 10% on air dry base for biomass fuel. The volatile matter content of biomass fuel is very high compared to other solid fuels like coal or lignite. 3 times higher than volatile matter of Indian coal. Almost. We have seen 23% for coal. Here we have the 69, 70%, around 70% for biomass fuel. Combustion of such high volatile matter fuels result in increase in flame length. Ignitability point of view is better fuel. Biomass fuel is a better fuel than coal because we have high volatile matter. Easily it can be ignitable. Ash content is vary from 1% to 15% compared to coal. You may start from 25% better coal, 25 to 50% ash content variation in the coal. So biomass fuel is and that respect is a cleaner fuel, resulting in ash content of 1 to 15%. So among the biomass fuels, sawdust, coir waste, bagasse have lower ash content, and straw husk fuels are higher ash content among the biomass fuels. Next one is ultimate analysis. Determination of carbon content. How much carbon content, how much hydrogen content, nitrogen, sulfur, and oxygen. This is called ultimate analysis or elemental analysis of the fuel, whatever way you call it. Carbon, hydrogen, how it is determined? You take about accurately 1 to 2 grams of biomass sample, but in the current of oxygen in a combustion apparatus, then carbon available in the biomass will be converted into carbon dioxide because of oxygen and high temperature. Hydrogen available in the fuel is converted into water, respectively. These two, CO2 and water, will be passed to absorbed by a potassium hydroxide or calcium chloride tube, known weight. So increase in KOH, result indication of CO2 content. Increase in weight of the calcium chloride tube is indication of water content, additionally water absorption. So from that, the increase in weight, you can calculate carbon, increase water, you can calculate the hydrogen content. So percentage of carbon is equal to increase in weight of KOH cube into 12 into 100 divided by weight of the sample and 40. The 44 is for CO2. If you have 44 CO2, then 12 is a carbon. So 44 12, the increase in weight, from this we can get the total CO2. Total CO2, how much carbon? So weight of the sample into 100, it will give you a percentage of carbon. Similarly, hydrogen, water weight is 18 molecular weight, 2 is hydrogen. For 80, you have 2. So increase in calcium chloride tube will give you total hydrogen content. For the weight of the sample, you can calculate percentage weight of hydrogen content in the fuel. This is the way carbon and hydrogen. Then nitrogen is very old technique by Gelder's flask. You take our 1 gram of biomass sample, heat in the sulfuric acid along with potassium sulfate catalyst. Then heated. After this, the excess sodium hydroxide is liberated ammonia. Excess liberated ammonia is treated with acid. Again, balanced acid treated with standard sodium hydroxide. So from that you can calculate from the ammonia, you can calculate percentage of nitrogen is equal to the volume of acid used into normality into 1.4 divided by weight of the fuel taken. So using this Gelder's flask, you can measure the nitrogen content of the biomass fuel. For that matter, not only biomass fuel, anything in nitrogen content, any organics, you can measure this same method. Then comes sulfur. Sulfur determined the old method, ESCA method, treating with ESCA method. Otherwise, you can do sulfur by bomb washing also. When you are doing calorific determination in oxygen bomb, all the sulfur will be converted into sulfate, SO3, and sulfuric acid. Then if you add barium chloride, barium sulfate will be precipitated. From that precipitate, you can find out how much sulfur content of the fuel. So bomb wash method it is called. Thereby you can measure the sulfur content of the fuel. Oxygen it is obtained by different percentage of oxygen is equal to 100 minus percentage of carbon, hydrogen, sulfur, nitrogen plus ash carbon. As we are doing in the approximate analysis, from that you can calculate whatever carbon, hydrogen, nitrogen, sulfur, oxygen in the fuel. That is called ultimate analysis of the fuel. For these are all conventional analysis. If you do by whatever method I told, carbon, hydrogen, nitrogen, it will take minimum for one fuel. I think it will take 1 or 2 days. Doing the Kildall method, then sulfur method, carbon, hydrogen, it will take maximum 2 days per analysis. Nowadays, our instrumental technique has come. Instrumental technique of carbon, hydrogen, nitrogen, sulfur method. The quantitative conversion of carbon, hydrogen, nitrogen, sulfur into their respective gases during combustion of sample at elevated temperature in oxide. As I said earlier, carbon will be converted to carbon dioxide measured by IR cell. Similarly, hydrogen will be converted to water measured by IR cell, infrared cell. Nitrogen will be converted to NOx. Again, through catalyst, it will be converted to nitrogen that is measured by thermal conductivity. Then sulfur, very high temperature, 1350 converted to SO2 measured by air. These instruments are calibrated using certified reference materials or NIST standard materials. So all the instruments are calibrated for carbon, hydrogen, nitrogen, sulfur. So by using that instrument, calibrated instrument, you can measure the ultimate analysis, carbon, hydrogen, nitrogen, sulfur by instrumental technique. Nowadays, as I told you earlier, in the earlier method, it will take per sample, it will take 1 or 2 days. Now, within a matter of half an hour, 30 minutes, you can complete carbon, hydrogen, nitrogen, sulfur per sample using instrumental technique. That is a very much advantage with the instrumental technique. This is a schematic diagram of carbon, hydrogen, nitrogen instrument. Here you take combustion tube. Here the sample is taken, carrier gas, oxygen is a carrier gas. So everything will be converted into CO2 and water and NOx. It passes to IR cell. Here you are measuring the hydrogen content. After it is passing through CO2 IR, here must be the carbon content, balance gas is going there. Aliquot of some sample is taken. It will pass through copper where the NOx is converted into nitrogen. Then finally nitrogen measured by thermal conductivity. So here we are measuring the hydrogen content. Here we are measuring carbon content. Here we are measuring nitrogen content. That's the instrumental technique. They have a carbon, hydrogen, nitrogen. Per sample, it will take minimum 12 minutes. Per sample of carbon, hydrogen, nitrogen determinant take 12 minutes. This is the instrument we got BHEL. So significance of ultimate analysis. So greater the percentage of carbon, hydrogen, better is the fuel quality and calorific value. Naturally, if you have more carbon, more hydrogen, calorific value also will be more. Also, higher percentage of carbon reduces the size of the combustion chamber. The amount of carbon and major combustion constituent fuel depends on the type of biomass. Nitrogen has no calorific value. Only thing is, if pollution point of view, it will give fuel mass. Hence, it's undesirable. Sulfur, although contributes heating only a little bit, it produces SO2 SOx, which are harmful in the effects of corroding the equipment and cause pollution. So this is the typical results of. So this is the typical results of ultimate analysis for the 7 biomass. I compared with coal also. The bottommost is the coal. If you see the carbon content of the biomass is almost similar to coal. See here you have 45%, 42%, 42%. Or straw fields maybe around 35, 36. Almost similar to coal as well as carbon is concerned. But interestingly, if you see the hydrogen content, coal you have 2.4% hydrogen, whereas all biomass fuels are almost more than 2 times. 5.26, 5%, 5%. So more than 2 times that of coal, the hydrogen content of biomass fuel. In that way, it's a better fuel. The nitrogen content, except groundnut shell, all biomass fuels are nitrogen content is lesser than that of coal. You have 0.45, 0.61, 0.72, 0.7, 0.2. Coal you have around 0.9. Normally coal you have 0.1, 0.8 to 1.2, 1.2% normally for coal. So except groundnut shell, all the biomass nitrogen content is very lesser than that of coal. Sulfur content similarly, very good advantages, very low sulfur content in biomass fuel. Except for bagasse and sort of point, other things are less than 0.1, close to point. Whereas coal, though this coal will give me a 0.36%, normally sulfur in the fuel varies from 0.5 to even 1.2, 1.2%, the Indian coal. So we have variation of coal, sulfur in coal is 0.3, 0.4 to even up to 1.2 we have, except some limited pockets where high sulfur coal. And on average, coal, sulfur value in coal is higher than that of biomass fuels. Biomass fuels, we have very less sulfur content. Similarly, oxygen. Am I audible, sir? Sir, am I audible?
Yes, sir, you are
Yes,
audible,
yes,
sir. You are audible.
Okay.
Yes, sir.
Okay.
yes,
So,
sir. Yes, sir.
so moisture content is almost say 5 times that of a coal. Almost you have more than 35% oxygen content. See, the carbon content of biomass fuels are almost similar to carbon content of Indian coal, varying 35 to 45% on year rate basis. Hydrogen content of biofuels about 2 times more than that of coal, indicating more reactive in nature during combustion than coal. Nitrogen content of biofuels, except groundnut shell, all other less than 1%, indicating lesser NOx emission during combustion, fuel NOx. So nitrogen content of groundnut shell is around 1.2 to slightly higher than the average nitrogen content of Indian coal. Sulfur content of all biomass fuel studies is less than 0.25, but the sulfur content of coal varies from 0.5 to as high as 3%. Some coals we have even high sulfur coals of India we have. So, NOx emission point of view, biomass fuels are better superior fuel. Then comes calorific value, heat content or amount of heat available. I told you the primary analysis, proximate analysis, and calorific value for any fuel. If you go to any power plant, normally they used to have these instruments, any power plant. They may not be having ultimate analyzer and all because sophisticated instrument and all. Or for all the course, commercial point of view, they have to conduct proximate analysis calorific value daily for each lot for payment purposes. So the payment is based on proximate analysis and calorific value. So all power plants will be having facilities to have the proximate analysis, to conduct the proximate analysis, calorific value of the any fuel. These two are very, very primary analysis for any fuel characteristics. So heating value or amount of heat available in a fuel is one of the most important characteristics of the fuel because it indicates total amount of energy that is available in the fuel, not only for commercial purpose also, payment purposes. The heat content of fuel type can vary significantly depending on the climate and soil in which the fuel is grown as well as other conditions. The most important noticeable trend is biomass fuel is wood. Wood is having very low ash content, tends to have slightly higher heating value than field crops. For example, you even see the wood, our analysis, you can compare probably sawdust. Ash content is around 1.79. Ash content of sawdust. If you see here, given some picture from various heat content, if you see all the things, pine wood, then poplar wood, then oak wood, all are the wood are having very high calorific value because of very much lower ash content compared to your grass. Which grass? See bagasse. So all the wood fuels are very high calorific value because of very much lower ash content. With respect to our fuel, whatever we have studied, see coir waste, groundnuts, all are, see coal is having 15.5 joules per kilogram, whereas more than the coal, the calorific value is the biomass almost. Similar or more than that sometimes. Except the straw fuel, straw has to be close to or slightly lesser than coal, but most of the biomass fuel calorific value is higher than that of the coal on air rate basis. This is a useful calorific value for available for boiler. This is the total calorific value determination in the laboratory. This is useful calorific value, net calorific value available for heat generation in the boiler. So the calorific value coir waste is 18.1 megajoules per kg on air rate basis, whereas the rice straw and rice husk is 14.86, 14.6 megajoules per kilogram. Of the 7 fuels studied, calorific value of the 5 fuels are above 17 megajoules per kg. Whatever fuel I have studied, the 7 fuels. The heating value of biofuels are either comparable to that of bituminous coal or sometimes better than the average Indian coal. As ash content increases, calorific value of biomass value decreases. Similarly, moisture content increases, calorific value comes down. Both high heating value. The HHV, LHV are same as that of gross calorific value or net calorific value. Both are same. Whether you call it high calorific value or gross calorific value or net calorific value or lower calorific value. Both are same. So as the moisture content increases, the calorific value comes down. Then biomass is made up of structure, mainly celluloid structure, lignocellulose structure. It mainly contains cellulose, hemicellulose, and lignin. The proportion and distribution of these components in the biomass is complex and very much important for its use in different industrial applications. So determination of cellulose, hemicellulose, lignin is very much important as part of characterization study. Cellulose is a high molecular weight polymer with molecular weight up to 10 to the power 6. sorry, 10, don't 106, 10 to the power of 6. The molecular weight that makes up the fiber and wood and other biomass. Hemicellulose are branched polymers, also polysaccharides consisting of shorter chain. Hemicellulose generally evolve light volatile. Most of the contribution of volatile matter coming from hemicellulose, producing less starch and char. So volatile matter contribution from hemicellulose more compared to cellulose or lignin. Lignin is amorphous and highly branched cross-linked macromolecular polyphenolic resin with no exact structure. Normally, lignin fills in the spaces in the cell wall between the cellulose and hemicellulose. This is structure, arrangement of the long one. These are all cellulose. These are all hemicellulose that is attached by the lignin content. These are the lignin content. Arrangement of cellulose. Not only my research, by other information is available for these biomasses. Cellulose varies from, say, this is the range. Then hemicellulose, then lignin content in the biomass. Graphs under 35 to 50, 10 to 40. Whatever studied for the subject to this by 7 biomass fuel, cellulose varies from, say, 39, 41. Hemicellulose 24% to close variation, 22 to 24%, except groundnut cell alone is having 28% groundnut cell. So hemicellulose groundnut cell alone highest among the biomass fuel studied. Lignin also 25.8 from the groundnut shell. Other things, straw fuels we have 13 to 14%, 15%. The lignin content. So groundnut cell alone is having some peculiar characteristics of the highest hemicellulose, high lignin content. This is the one observation I could make it. Groundnut shell. So the cellulose content varies from 31 to 44%, hemicellulose 20 to 28%, lignin 12 to 26%. The lignin content of straw fuels is lower compared to other fuels. The lignin content of shell fuels high, say for groundnut cell 26%. Other reports say hazelnut cell 22%, coconut cell 29%. So lignin content all the cell biomass are higher. Biomass fuels in general, although consisting of the same major constituent, have some difference in their composition. Heating value of hemicellulose is the highest, followed by lignin and cellulose. Next one is flammability index of the fuels. That's another characterization technique. Flammability means ease with which a fuel may be brought into state of visible sustained combustion. That's called flammability. The test involves firing a 0.2 gram of ground fuel sample, finely ground fuel sample, in an oxygen atmosphere through a preheated furnace. The temperature of the furnace is increased incrementally until the point where reach of our interest. Then fuel, at which the fuel ignites, that is called flammability index. Once the preset temperature reaches, the solenoid will switched on and allow the sample to be blown rapidly into the ignition tube. The appearance of flame, it's a ignition point. So this is the instrument, flammability testing. This is the furnace. Here you are taking the sample, finely ground sample. Here there is a solenoid valve. Here oxygen is cylinder under pressure. Going on, increase the temperature of the furnace as you decide. Once you decide temperature is, just open the solenoid valve. Through oxygen pressurization, the sample will be pushed through these tubes. There you watch the flame. If there is a flame, yes, visible flame, that is the ignition point. Otherwise, you increase the temperature for another 5 degrees. Going on, increase the temperature right from the ambient or from 200 degrees you start. At what temperature you are getting a stable flame? Each time you got to put the sample here, and then operate the solenoid valve. So flammability refers to the lowest temperature at which a visible sustained flame appears. The flame appears here, that is called flammability. So if we compare the flammability temperature for all the fuels, it varies from almost close to 350 degrees, 350 to 380 degrees. Coal we have 500 degrees. So flammability point of view, biomass fuels are better fuel, easily ignitable because of obvious reason, high volatile matter content. So flammability refers to the lowest temperature at which a visible sustained flame appears. The flammability index of biomass fuel is very narrow range, 350 to 400 degrees C. Flammability index of biomass fuels less than the fossil fuels, and then stability or stable combustion can be easily achieved at comparatively lower temperature than coal. Biomass fuels are more reactive with respect to flammability characteristics than lignates or coal. As hemicellulose content increases, flammability index decreases. Higher the semicellulose content, more volatile. So naturally, flammability index or temperature will come down. Easily ignitable. Next characterization: fuel size and density. The size and density of the biomass fuel particles affect the burning characteristics of the fuel by affecting the rate of heating, rate of drying during combustion. So size and density plays important role with respect to combustion. So fuel size also dictate the type of handling equipment that is used. Wrong size of fuel will have impact on the efficiency of the combustion process and may cause jamming or damage to the handling equipment. The size of the particle, fuel size particle. Smaller sized fuel is more common for commercial scale systems because of smaller fuel is easier to use in automatic feeding system, and also allow the finer control of burning rate. Smaller the fuel, you can control the burning rate very fine. Thereby it's easier. So very strength and bulk density. Higher the size you have, the bulk density will be more. So fuel size and density probably most overlooked factor affecting the fuel performance and should be given careful consideration when selecting the fuel type. Biomass can also be delivered to power plant in bales. For example, straw fuel in the form of bale, that can be supplied delivered to power plant. This format is mostly used in straw and it requires special equipment to remove the strings and break up the bale. Or plant may be designed specifically to burn bale. Bales are relatively easy to transport, have a good bulk density. They can also be stored in the open for shorter periods of time. Modern large bale can weigh up to 300 to 500 kg. Dry biomass needs to be stored under a cover to avoid self-heating. Self-heating is another important aspect. Decomposition, growth of spores and fungi. Lower bulk density, 200 500 compared to coal means volume to store as well as physical transport capacity will be large compared to coal. Coals are high density fuels compared to biomass fuel. These are low density fuels, biomass. So methods to increase the bulk densities by pelletizing or briquetting. These are the techniques available for increase the bulk density of the fuel, which also improves the bulk handling properties of the fuel. And dried pellet briquette will be have a higher calorific value. That's another advantage, but it is more expensive. Briquetting or pelletizing is more expensive. Pellets and briquettes are generally more cost effective to transport due to their higher bulk density. See, 600 to 700 kg per metric. From somewhere around 200 300, you could make it to 600 to 700 kg per metric bulk density by pelletizing. Less prone for hang up in the bunkers or conveyors. These are the pellets, food pellets. Pellets are biomass compressed to small cylinders with a typical diameter of 5 to 15 mm and length at 10 mm. They have higher standard bulk salinity and the clean and dry also comparatively because of pelletizing, all the moisture gets removed. There will always less than 10% consistent quality you can get it. Next technique is characterization technique, thermogravimetric analysis technique. The thermogravimetric analysis measures change in weight of a material as a function of temperature or time in a controlled temperature program at atmosphere. Here, while heating the sample, ultimately through combustion, what we are doing, heating the sample fuel. While you are heating the fuel, what happened to the mass weight? That we are studying with the TGA technique. You cannot study the mass loss within the boiler. There you can simulate the conditions of heating in the laboratory instrument, that is TGA. You have the furnace and balance both together. So you measure the change in weight as a function of temperature or time in the controlled heating. So that is called, if you are studying mass versus time, it is called thermogravimetric analysis. This is the thing. While heating, the mass comes down. This is a weight marker. It is called thermogram. Weight loss versus time is called thermogram or TG. Other one is, if you study the rate of weight loss versus time, is called derivative thermogram, DTG. This is a derivative. The green one is TG, thermogram. Here you see the weight loss. This is a derivative thermogram. This is a weight loss, again derivative thermogram. So this is the thermogram, TG, green one. Blue one is derivative thermogram. Rate of weight loss versus time or temperature. So there's a difference between thermogram, derivative thermogram. This is the, again for the coal chart, weight loss thermogram. This is the derivative thermogram, blue one. So burning profile technique for assessing the ultimately we are interested in the combustion reactivity of any fuel, whether coal or biomass, any solid fuel, the combustion reactivity, the time, speed, rate at which you are handling the combustion, heating. So burning profile technique for assessing the reactivity where derivative thermogram output signal from a thermobalance system is plotted against the temperature. That is called burning profile test. So fuel is heated in a concentrate and a flowing stream of air. In all TG experiments, around 10 milligrams of biomass samples is used. Heating continued till the combustion got completed. The burning profile or DTG of all biomass are also shown here. So the first one is for coir waste. I have not shown here TG, only derivative thermogram. That is of our interest. I have shown here all the derivative thermogram of the 7 biomass fields. This is for coir waste. Here you can see here two interest peaks, sharp peaks. So first peak is initial peak is very small peak, we forget it. These are the two characteristic peaks for coir waste. Heating rate is 15 degrees per minute. Atmosphere air for coir waste, this is 2 profile. Similarly for groundnut shell again, there are two peaks. But if it is a groundnut shell, there is a time lag between this and here it comes down, immediately it goes up. Whereas there is a time lag here. I will explain here why there is a time lag. This is between coir waste and groundnut shell. Next one is bagasse. Again, there are two peaks. And sawdust. Again, there are two peaks. This is for wheat straw. The second peak is some is overlapped peak. The rice straw, similar to straw. Straw fuel, both the straw is behaving similarly. Then this for rice gas, second peak. Whereas coal, you have only one peak. Can you now understand? The biomass fuels and coal, same run, same heating rate is 15 degrees per minute. Air, only thing is coal. All biomass showing two characteristic peaks, whereas coal you have only one peak. So there is a marked difference in the burning profiles of biomass and coal. What is the difference? All the DTG of the biomass fuels characterized by two distinct peaks. Their area under the peak measured are in agreement with the first peak is combined for the volatile matter content and fixed carbon in the second peak. So both volatile matter and fixed carbon in the path of the second peak are respective. So the initial peak at temperature 100 degrees corresponds to release of moisture. So now you see, you go here, yeah. So this is the release of moisture. This one peak is related to combustion of volatile matter. This peak is related to combustion of fixed carbon. The main combustion peak for coal is preceded by a shoulder which is partly attributed to combustion. If you see the coal, there is a shoulder-like thing. This is maybe attributed to volatile matter combined. So this is the thermodynamic analysis of the biomass fuel, from which now each burning profile curve is marked by a few characteristic temperatures. You can study the more elaborate manner the burning profile, the characteristics. So each burning profile curve is marked by a few characteristics. Only VMIT, temperature at which volatile matter weight loss begins. That's VMIT, initiation temperature for volatile matter weight loss. Then VMPT, temperature at which maximum rate of weight loss. VMPT. Then temperature at which the rate of VM close ends. VMCT. Then fixed carbon IT, FCIT. Temperature at which the rate of fixed carbon loss begins. Then temperature at which the rate of fixed carbon is maximum called FCPT. Last one is BT, burnout temperature at which the weight loss becomes constant, indicating completion of burning. That is called BT, complete, burning completion. So this is what VMIT, initiation of volatile matter, start of volatile matter, temperature at which volatile matter is maximum, VMPT. Here you can call it a VM completion, then start of fixed carbon, maximum temperature at which fixed carbon burning rate, then BT final temperature. There all the completion here called BT. So these are the all the temperature data burning profile for the all the biomass fuels. So initiation of all volatile matter combustion, initiation starts around say 195, this way 192, around 220 for all the fuels. Then maximum also around 320, maximum volatile matter combustion. Here, if you see VM completion and fixed carbon initiation, almost same 370, 370, 380, 380, except groundnut cell. Groundnut cell, there is a time lag between VM combustion and fixed carbon combustion. Here, 352 ends, again it starts around 392. There is a time lag between these two VM combustion and fixed carbon combustion with respect to groundnut cell. That's one thing visibly we can see. Here, and that's what I have shown you. Definitely, there is a time lag between groundnut cell VM combustion and the combustion of fixed carbon. There's a time lag. That's what's shown here. Then among the fuels, fixed carbon burnout for rice gas is the highest. Among all the fuels, this is the rice gas. Complete burning is final temperature 570 degree compared to other. So the loss of VM started in the range of 180 to 230 for all the biomass fuels that we have seen. Volatile matter initiation, combustion initiation. The peak temperature at which the volatile matter is between 310 degrees, 343, that's also an error rate. The volatile matter peak temperature for bagasse and sawdust are higher than that of the fuel due to more VM content. For all fuels except groundnut shell, the two combustion peaks close to each other. For ground cell, there is a time lag between the two. The reason being the peak rate of VM combustion for highest for grounded cell and completion of VM combustion is faster rate, because you have seen here it completes at 350 degree. Maybe 350 degree may not be sufficient to initiate fixed carbon combustion. So it has rate up 300 degree to start initiation. So here VM release and combustion for grounded cell is very fast. That's one of the indications. VM release and combustion is so quick for grounded cell. That's why there is a time lag. The fixed carbon initiation for all the fuels in the range of 360 to 380 except groundnut cell. Fixed carbon peak temperature for all the fuels except rices is the range of 410 to 435 degrees C. Two overlapping fixed carbon components we observed for rice straw and wheat straw, that we have seen overlapping peak. These are rice straw and wheat straw. The burnout temperature for biomass fuels are in the range of 440 to 470. The burnout temperature fuels follows this order. Rice is the highest, followed by rice straw, wheat straw, groundnut cell. It indicates that among the biomass fuels, complete combustion will be difficult for rice. Comparative sense, all the biomass rice's combustion will be very difficult. Complete combustion will be very difficult. I don't know how many of you observed, whenever rice is given, you end up with a black ash, not white ash. Very difficult. Unless otherwise we have very slow combustion, you end up white ash. Otherwise, the rice will result in black colored ash. Complete combustion is very difficult for rices. We go for higher rating. Very slow combustion will give you result to white ash. Otherwise, rices will result in high carbon content. So fuels with the higher BT may result in more unburned carbon with actual combustion, especially rices. So differential scanning calorimetry. The differential scanning calorimetry DSC is one of the most frequently used technique in the field of thermal characterization of solid, coal, biomass, thermal characterization. DSC measures the TGA, we are measuring the weight loss, nothing to do with the calorifical or heat content. Whereas DSC measures the differences in heat flow into the substance and reference as a function of temperature, while both are subject to controlled temperature program. So DSC provides access to accurately thermodynamic data as well as information regarding reactivity and phase transmission and heat flow. So in DSC, these are the exothermic peak heat release from the sample. These are absorption by the endothermic peak heat absorption by the sample. So useful to study the aspects related to reactivity, heat transfer associated with the pyrolysis and heat combustion. So DSC run for all the biomass samples are carried out at the dynamic heating rate of 15 degrees C per minute from ambient to till the heat flow from the field is completed. All the DSC thermogram of the biomass samples are characterized by agile to distinct exothermic peak, similar to TGA. The initial endothermic peak is below 400 observed to relate to endothermic peak, initial peak. It's a release of moisture. The other two exothermic peaks related to heat of combustion of volatile matter and fixed carbon. You can see here. This initial endothermic peak is due to moisture, removal of moisture, endothermic peak. Whereas these two exothermic peaks are related to combustion of volatile matter and fixed carbon. So heat release profile of coir waste, heat release profile of groundnut cell. Any peculiar observation, participant, can you make it compared to TG? See, these are all heat release profile of, again I will show you. This is for bagasse, this is for sawdust. Now for comparison purpose, I am putting here TG, coir waste. Any peculiar observation you are making? compared to TGA and DSE? And any participant can answer.
Participants, you can unmute yourself and then give the answers.
What's the difference between DSE and TGA? By observing the plots. This is for TGA plots, TTG plots. For the same swim sample I am giving here for coir base and ground nets. Can you see the height of the peaks? This is the VM peak, heat release due to VM, heat release due to fixed carbon. Fixed carbon peaks are higher than volatile matter peak in DSE. Here also for DSE. Whereas in TGE, the other way around. VM peaks are higher than the fixed carbon. Are you able to see? Are you able to see? Are you able to see? Are you able to see?
Yes, sir. Yes, sir.
Yes, difference.
Sir, yes, sir. Yes, sir.
Yes. Okay. So this is for other biomass fuels, DSE of wheat straw, rice straw. These two follows similar to TG. Rice straw, wheat straw, rices. See this observation. So the DSE profiles reveals the intensities of the heat release by fixed carbon fraction of fuels. Coir waste, groundnut shell, bagasse, sawdust are more than that of the intensity of the heat release due to VM. That is one of the peculiar observations with respect to TG compared to TG. But wheats are rices show the reverse trend. The heat release due to VM is lesser than that of the VM. The higher DS intensity for second peak for the coir waste, groundnut and bagasse sand is due to highly porous structure of the chars of these fields exhibited by S. We will see the SEM picture. Once volatile matter is released, we call it a char. Once volatile matter is released, we call it a char. The char of coir waste, groundnut shell, bagasse, sawdust are highly porous. If you compare the rice husk, rice straw, and rice husk, this is different. Not so. If you see a SEM picture, you will understand. Because a highly porous structure, heat release from higher waste, bagasse, sawdust are so quick for fixed carbon. That is why the intensity is going high. So such a differences in intensities between the field not observed in TTG. All the 7 fields, height of the second peak was lesser than that. That's it. Because of that, because highly porous structure of the char particles, the heat release much higher rate. That's why we are seeing the difference. Now we will come to combustion characteristics of the biomass char. So whenever a fuel particle injected into the furnace, whether solid fuels, whether biomass or coal, any solid fuel enters into the furnace, the first one is release of moisture. This is the first activity, release of moisture. Second one is release of volatile matter and combustion. Volatile matter release and burn. Third activity is, once these two are removed, it's called char. Char nothing but fixed carbon and ash. So next is burning of fixed carbon burns slower rate, much higher temperature. This is the last one. This is a combustion process in the furnace. So in the fuel particle, first devolatilization, volatile removed. It takes some milliseconds. Once volatile is removed, balance is char. Volatile, you have a homogeneous combustion. Then char is a solid, you have heterogeneous combustion. This combustion process will take few milliseconds. This volatile matter combustion. Whereas this heterogeneous combustion of char particle will take 1 to 2 seconds. Among these two processes, this is a very slow process. Because it will take only millisecond, because gas combustion, homogeneous combustion. Volatile nothing but a gas. So it's a much faster rate. milliseconds. It will take few seconds. It's a slower heating rate. So combustion of any solid fuel can broadly separate into two types of reactions. Fuel is converted to BM and char. BM is a gaseous combustion product. In char, leads to gaseous combustion product plus ash. When the solid fuel is injected into the combustion chamber, solid fuel first heat up rapidly and devolatilization of volatile matter occurs in the fraction of a second, and subsequent combustion of this gaseous matter is instantaneous and rapid. Because volatile matter, the last activity is combustion of char. It will take 2 to 3 seconds. Since char combustion is a slow process, it becomes a critical step in determining the rate of combustion. So rate of combustion is decided by slow process. So if you want to study a reactivity of the fuel, don't study, you eliminate VM, because it is sufficient you study the char combustion. Because char combustion is going to be a determining step. The samples of char residues after volatile matter determining the biomass samples are collected. Then we are studying the char kinetics using TGA. Same, the reactivity pattern. Earlier we have seen the raw fuel. Now we have prepared the char after removal of volatile matter. Then char studies were made using TGA. So thermodynamic analysis are carried out for biomass char samples in a dynamic non-isothermal mode with the heating rate of 15 days to be met in presence of air. The derivative thermogram of only for simplicity I am representing only 4 biomass char samples. This is for coir waste char, sawdust, rice straw, and rice husk. The TTG profiles for these 4 charts. So these are characterized by again VMI initiation of char combustion start, char combustion peak rate, and burnout temperature, final temperature. These are the 3 or 2 by 4 characteristic temperatures. Same thing. Char combustion. Here, if you see some useful information, if you see this number among all the fuels, rice has the burnout temperature highest 648, nowhere here 537, 518, 540, 565. This road 648. Very well clear indicates that rice's combustion is relatively very difficult. Complete combustion of rice will be difficult compared to all the other fuels because of 648 degrees. This is one of the important conclusions you can draw. So based on the burnout temperature, you can which fuel can be burned completely more easily. So you can see here groundnut shell, very easy to. It is close to even 580, followed by coir waste. Among the fuels, sawdust, rice is the highest one, very difficult. So the review of the data indicates the temperature profile of the rice is exceptionally different from that of other fuel charts. While thermal decomposition picture carbon of other char samples start around 4 to 3 point, decomposition of rices start around 530 only. Highest fixed carbon initiative for rices suggests that it will be very difficult to initiate char combustion rices compared to other fuel. Based on these char kinetics, the char reactivity TTG data, we also made kinetic calculations. The rate of combustion of char is given by rate of reaction. What the chemistry term, rate of reaction or rate of combustion given by dW dt by equal to K into W minus W. Here W is weight of the undecomposed char. This is the ash. Weight is the weight of the ash at the end of the combustion. So W minus W will give the concentration of the reactant. Here weight of the undecomposed char. Here final ash. So W minus W is the concentration of the reaction. So rate of reaction is proportional to the concentration of the reactant. K is the combustion rate constant, which is defined by Arrhenius equation. K is equal to A into E for RT. ln K is equal to ln E into minus E. The E is activation energy. R and T as a universal gas can absolute temperature respectively. So from this you can draw from TTG profile. This you can collect it from the TG. Both are available. See, for example, you can see here. Those for cold char. Here is your DTG, dW by dt, derivative by dW. For any temperature you take, 400, this is a dW dt, corresponding you have the W. Final WF you have here. So all the three data, W here, WF from here, dW dt here from here. For each temperature you can calculate. So for each temperature you can calculate, it's the temperature inverse. The W you can calculate from TG, dW by dt you can calculate from derivative thermogram. dW dt by W will give you K, UK. So log you can calculate for log K for each temperature. Then temperature versus log we can plot. From TG, DTG data, K is calculated for each star sample for different temperature. Plots of log K versus 1 by T give two biomass are shown here. For high ash biomass charge, two regions of striking linearities were observed. High ash in the sense the rice straw rises wheat straw comparatively. For all the 7 biomass, I rated 3 high ash. Here we have 14%, 15% ash content. So for high ash biomass fuel charge, two regions of cycle linearity were observed from the plot, but for low ash, only one linearity was observed. The reason being, it's in this chart. For coir waste, low ash, we are getting. Yes, sir. Yes, sir. Hello? Hello, there is some disturbances. Hello? Hello?
Sir, it's been muted, sir. You can continue, sir.
Okay.
Sorry for that.
Yeah. For coir waste charge, you have one linearity, whereas high ash, the rices, you have two regions of linearity. That's what I want to explain now. So for a high ash fuel charge, you have two regions of cycling linearity, whereas low ash we have only. The reason being, for low ash fuels, you have very high fixed carbon, higher waste are 91 for the char content. Char, highly porous, I already explained. Because a highly porous structure with a large surface area, only chemically controlled mechanism taking place for low ash char. Because a highly porous structure, large surface area, only chemically controlled mechanism may be operating. That is why we have one linearity. Whereas if higher charge, in addition to chemically controlled mechanism, there is a because of large, it's not highly porous. Gas phase diffusion control mechanism also may be operating. That is why we have two linearity, two regions of linearity with the two activation energy. So for high ash fuel, we have two activation energy. For low ash fuel, we have one activation energy. Whereas you can ask one question, for a groundnut shell, we have another second. The reason being, char we are preparing at 900 degree. See, char means removal of volatile matter. Volatile matter can be removed at 900 degree. When I am subjecting groundnut shell at 900 degree for the removal of volatile matter for the preparation of char, at 900 degree, there is some surface melting of char. So then, like this, the high ash fuel, here also, pore diffusion control also is because of some melting characteristics of surface over the surface. Gas diffusion control also plays a role. That is why for groundnuts alone, you go second region of linear, similar to high ash fuel. So this is activation energy for the all the 7 biomass fuels. So char oxidation data for the biomass fuels revealed that combustion reactivity of high ash fuels straw, husk is lower than that of the lower biomass like coir waste, bagasse, sawdust. The poor reactivity of rices char in non-isothermal conditions indicates 100% carbon conversion in rices will be difficult compared to other fuels, and combustion of rices may produce more unburned carbon in actual combustion. Coir waste, bagasse, sawdust are more reactive and almost equal at lower temperature. So higher furnace temperatures are required for to make the carbon conversion more efficient for straw and as well. So if you are planning for firing straw husk fuels, you need higher temperature. Whereas the other fuels, even low temperature. That is why for these fuels, low temperature gasification is a better route for coir waste, for sawdust. If you want to use liquid fuels, this coir waste sawdust, low temperature gasification is a better route compared to complete combustion. The activation energy for the char combustion data indicate the combustion is predominantly chemically controlled for fuel like bagasse, sawdust, and coir waste due to highly porous structure, whereas the diffusion mechanism is the controlling factor for husk and straw fuels due to non-porous structure, which is reflected in the higher activation energy. On a comparative basis, the likely pattern of unburned carbon level for actual biomass fuels studied based on their char reactivity, rice husk will give more unburned carbon, followed by straw fuels, then coir waste, bagasse, and sawdust. This is a conclusion I drawn from. This surface area, you can see here. Surface area char. You can see the grounded surface areas come down. Because I told you, char preparation at 900 degrees, there is a partial surface melting because of 900 degree. That's the surface area of char of grounded is lower value. Whereas coir waste, bagasse, and sawdust are high surface area, highly porous structure. These are all comparatively lesser surface area. See the SCM analysis. Only I am showing the picture. See the coir waste. Lot of valleys. So complete combustion of the entire surface area. So total surface area is available for combustion here. Coir waste. You see the lot of valleys. There is a 2000 magnification of coir waste char, the SCM. Whereas groundnuts, you can see some part of melting. Both all are prepared at 900 degrees. All the chars are. See the bagasse, you can see the lot of pores. Similar for sawdust. So these fuel 1, 2, coir waste, a highly porous structure. Lot of surface area is available. That is why now you can explain. Now you can confirm that the DSC profiles of second peak more intense than first peak because of highly porous structure. The entire surface is available for heat release with respect to coir waste, bagasse, and sawdust. If you consider wheat, straw, rice, these are all not highly porous. Rice is also not highly porous. Now we'll move on to rice biomass as characteristics. So we are more so far we have seen the combustion reactivity, so many things. So the characteristics related to that TGA, DSC, flammability, proximate, ultimate, calorific, everything related to combustion. Now we shift to as characteristics. Not all the problems will be facing because of biomass. So the inorganic materials biomass can be divided into two broad categories, two factors. One is inherent inorganic material, which exists as part of the organic structure of the fuel and is most commonly associated with the functional group of oxygen, sulfur, nitrogen. Inherent inorganic material. Something like chemistry, you can understand COONA, COO potassium, or amine, NH2 something attached to amine. So these are all inherent inorganic materials. These organic functional group can provide suitable sites for these inorganic species to be associated chemically in the form of cations or chelates. So these inorganic species present in very fine particulate form within the organic structure. The second one is extraneous inorganic material which has been added to the fuel through geological processes or during harvesting, handling, mostly added on this extraneous inorganic material. During handling, sampling, processing. So these are the two broad fractions. One is inherent inorganic material, one is extraneous inorganic material. And that is a broad fraction. But how to species, elemental species in a useful category, how the inorganic has content. One is water soluble, other one is organically associated, third one is precipitated as relatively pure compounds in crystalline amorphous forms. These are three broad categories. Speciation. You can see here, these are all inorganic available in the biomass sphere in a water soluble form. If you consider sodium, sodium nitrate will be there, sodium chloride, both are soluble, water soluble. Potassium, potassium nitrate, potassium chloride. Calcium, calcium nitrate, calcium phosphate. So these are the things available in the biomass as a water soluble form. Ionic. Water soluble. The second category is organically associated. For example, magnesium available, or manganese. These are things organically associated with the biomass. Third one is as precipitate as a pure compound. There is calcium oxalate or phytoferritin or phytates or phytolites. For example, silica. These are come as a precipitate. So these are broad speciation characteristics. The speciation of inorganic materials higher class according to the class of either water soluble or organically associated or precipitated. These are the three major types. The data indicate clearly the inherent inorganic materials in the biomass material, that is alkali metals, water soluble, sulfur, phosphorus, chlorine tend to present as a largely soluble form. Most in the inorganic. Silicon is present predominantly silica in the precipitated form, third category. Or alkaline earth, calcium and are more complex, can be present in number of forms. The extraneous inorganic materials also present in many forms. So anything extraneous metals of water soluble in many forms. In most cases, it takes the form of contamination from the sand, soil, or other mineral materials. For many biomass materials, significant portion of the inorganic materials is volatile. Here comes the very important point. All the participants, please pay attention. For many biomass materials, the significant portion of the inorganic materials is volatile at the conventional ashing temperature of the coal. Coal, we are doing ashing at 800 degree. In coal analysis, the ash proximate analysis for anything, ash preparation for anything, the ash content is carried out at ashing temperature of 800 degree. Whereas the ashing temperature of 500 C has been adopted for standard for ash content of biomass determination because to avoid underestimation of ash content due to loss of volatile inorganic. If you do ash biomass ash at 800 degree, some of the ash may become volatile. Escapes. So real ash content you will not measure for biomass if you do ashing temperature at 800 degree. That is why for all the biomass fields, the ashing temperature should be around 500 in order to avoid the loss of volatile inorganic compound. Similarly, for ash analysis, the iron oxide, silica, for ash analysis in the ash, the biomass material normally wet chemical digestion for raw biomass is taken rather than ash content. If you take the ash for ash analysis for the element for composition of ash, silica, alumina, iron oxide, calcium, magnesium. If you want to determine these components in the ash, you do not take ash. If you take the ash for some of the ash may go as a volatile. So real composition you cannot get it. So that is why raw biomass is taken for rather than laboratory prepared as is preferred because concerns about the potential for loss of volatile inorganic compounds. Of course, nowadays ICP-AES technique has come there. All the acid will be converted into plasma. Whether it becomes volatile or not, everything will be captured in ICP-AES technique. Previously, you want to study the composition of the ash, you would take the raw biomass rather than the ash. Nowadays, it is ash accepted for ICP-AES technique. The ash content of the majority of the biomass materials, with the exception of poultry litter, are around 5 to 7% on dry basis. Wood material having less than 2% as you see the sawdust. Straw and grass materials and solid residues from vegetable oil producing industries have ash content 5 to 15%. We have seen the rice straw, wheat straw, rices are around 14%. All the biomass assets tend to be rich, fairly similar suit of inorganic species. The compounds of calcium will be there, potassium will be there, silicon, phosphorus, magnesium. Clean wood are rich in calcium, silicon, and potassium. In general, there are three types of biomass ashes have been described by Bryce. Three types of biomass ash types biomass. You have high silica, high potassium, low calcium ashes with low asphyxiation temperature. Second one is low silica, low potassium, high calcium ashes. The third one is high calcium, high phosphorus ashes. For example, if we see here, this is for composition of the 7 biomass field, what are my project, my research report. You see here, the bagasse, rice straw, rice husk. These two, bagasse, rice straw, straw field, rice field. High silica, low calcium. See, silica is 70%, wheats are 70%, 70% rice percent. So high silica, low calcium. Bagasse is 6.6%, 6%, 3%. So high silica, low calcium. The groundnut cells have that low silica, high calcium. Groundnut cell, low silica, calcium, high calcium, 17% compared to other things. 17%. Then coir waste, high potassium, low calcium. Potassium here 32% for higher waste, whereas calcium. So different types of, that's it. The initial beginning I told you, all biomasses are not same, difference in quality. You such type of different types of biomass ashes. Then next characterization is chemical fractionation technique. Developed originally for the characterization of inorganic components of coal, has also been applied for characterization of biomass material. The procedure involves treatment of small amount of fuel, not ash, fuel, by standardized leaching process. The leaching reagent employed in this process are either water as a leaching media or ammonium acetate or hydrochloric acid. These are the three leaching standard solvents. Four fractions normally obtained. One is water leachable compounds, principally alkali metal salt, sulfur, chlorine compound. The second one is ammonia acetate leachable compounds, which are generally associated with the organic fraction. Aqueous cations are chelate. Third one is acid leachable compound, generally carbonate sulfate. Last one is water leftover residue, solid residue leftover, mostly silica silicate. So water soluble, ammonium acetate leachable, then acid leachable, then leftover residue. It is generally considered that the water acetate leachable are more readily released to vapor phase. Now this is the important point. Which are the constituents leachable by water or acetate, organic, are easily released to water vapor phase during combustion. So most whichever component released by vapor phase can be easily leachable by water or ammonium acetate and form a very finest aerosol fraction of the air generated from the biomass at elevated temperature. So if you want to study what are the vaporous fraction of the inorganic constituents present in the biomass field, you have to go for water leachable studies and ammonia acetate leachable studies. So whatever comes out of these two leachable fractions are responsible for vaporous fraction of the alkali. Last one, acid-soluble residue fractions are not considered to be released during vapor phase, during most thermal processes. So if you see some of the results here, forest residue. So if you say this is a water leachable, this is a ammonium mustard leachable, hydrochloric acid leachable. This is less. So calcium, you have forest residue, substantial amount of ammonium mustard soluble. Similarly, potassium, wheat straw, calcium and potassium. Bark, calcium, potassium. Coal, nothing is there. No calcium. They are all very insignificant. So the wood chips, again calcium, potassium. So calcium and potassium, examples of basic chemical facts in data for a range of solid fuels. So these results illustrate differences in the leaching behavior of biomass materials and conventional fuel. Coal. For bituminous coals, very little of the inorganic material in the fuel are generally only sodium chloride was found in the water and acid soluble fact. Only very small amount of sodium chloride with respect to coal. Whereas in biomass, lot of calcium and potassium comes out as a vaporous form. In biomass materials in general, significant higher levels of water and acid soluble material, which majority are potassium, chloride and calcium. These are coming out as a vaporous form from the two soluble fraction of water soluble and ammonium mustard soluble. Peat straw and forest residue, one, whatever we have seen here, significant part of silica also, water and acid soluble. This is one of the characteristic technique I have adopted for my research project. So we are so far we have seen the water soluble fraction, ammonium mustard soluble assumed to be highly vaporous. Whatever salts comes out is really vaporous. Instead of going for indirect method of water soluble, ammonium soluble, why don't we measure straight away vaporous alkali? That approach what I made in, see this is oxygen bomb. Whatever you're doing calorimeter, bomb calorimeter, you are using the oxygen bomb. There you are taking the fuel, burning for oxygen, you are filling with oxygen and burning. I have collected after burning, I have collected all the fuel gas after completion of bomb calorimeter reading. I have collected all the gases passed through a DM water. This DM water and this DM water, both sample I collected, I analyzed for vaporous alkali. It gives a direct measure of vaporous alkali because in bomb calorimeter experiment, the combustion temperature inside will be around 213 degrees. Straight away, then everything, all the vaporous portion will comes out after 12 degree, 13 degree centigrade. Trying to measure the alkalis from these two washings of the water, DM water, this water. So whatever, that's also I added here vaporous alkali. Straight away collected from bomb washing. So water soluble, acetic acid soluble, hydrochloric acid soluble fraction of the sodium oxide, potassium oxide. These are the things I have measured during my research project. So this is a direct measure of vaporous alkali. These are all indirect method of water soluble, acidic soluble, indirect method. We assume these are all vaporous alkali. Instead, directly vaporous alkali is measured by bomb washing method. So based on this calculation, highly vaporous sodium for coir waste, groundnut cell, sawdust. If you see coir waste, sodium around under 106%. Whatever sodium is available, completely vaporous in coir waste. Similarly, groundnut shell. Whatever sodium available in the groundnut shell, completely vaporizable. Whereas sawdust, so 96%. In case of potassium, 70% available potassium is vaporizable. Groundnut shell, 87%. Whatever potassium available in the groundnut shell is 87% vaporizable. Here all 49%. Straw, weeds are 40%. 40% is vaporizable content of potassium in available. The last one, the ice fusion temperature. Observation of temperature at which cones are prepared. Observation of temperature at which cones are prepared from the ash When it is heated, it passes different stages of fusion or flow in a specific rate. See, for example, this is a ash cone, prepared raw cone, prepared for the biomass ash. When it is heated, initially the tip melts. That's called IDT, initial deformation temperature. Before heating, initial deformation temperature first one. Secondly, when the ash cone comes like this, when the height of the cone is equal to the width of the peak, height equals is called softening temperature. Then height becomes half of the width is called hemispherical temperature. Last one is flow temperature, fluid temperature. See, these are four different stages of ash fusion temperature. Initial deformation temperature, when the tip melts, then softening temperature, hemispherical temperature. These are the four temperatures required for deciding the boiler. At what temperature the ash melts. So indirectly, ash fusion temperature measurement of melting characteristics of the ash. This is normally adapted for coal. Same thing we are adapting for biomass fuel also. The standard ash fusion test, which has been applied for the fusion behavior of coal ashes for many decades, is based on determination of 3 or 4 key temperatures, whatever I told you, initial deformation temperature, softening temperature, hemispherical temperature. Developed specifically the aluminosilicate coal ash system, the application of this procedure to biomass fuels, most of which are non-aluminosilicate. You can see the biomass as there is no alumina. So biomass as a non-aluminosilicate ash. So application and the technique available for biomass is what you are think. Very cautious approach you have to make. Many biomass ashes melt at temperature less than 1000 degrees. Another important parameter. Most of the coal ashes melting will be around say 1200, 1300, 1400. Here, many of the biomass ashes melt at temperature less than 1000 degrees, and significant amount of ash calcium is highly volatile also. That we have seen that significant portion of the inorganics is going as a volatile. So heating and hence AFT technique should be treated with great caution. When you are doing AFT for biomass ash, something is volatile. There is no melting and all. So adaptation of AFT technique for biomass with great cost. So these are the results of the biomass ashes for the ash fusion temperature. You can see here coir waste, IDT and softening is less than 1000 degree for coir waste ground cell. See 830 degree. Ground cell 760 IDT. Less than 1000 degree. So these are the ash related problems. One is slagging. Slagging indirectly you can call say in general terms deposition and corrosion and erosion. These are the two issues ash related problems: deposition, corrosion, and erosion. Deposition are two types: only slagging type of deposition and fouling type of deposition. Deposition in the boiler sections where radiating heat and dominant we call the slagging type of deposition. Deposition in boiler convective zone is called fouling type of deposition. These are two types of deposition behavior. Second problem is corrosion. Reaction of the metal with the component from ash deposit or flue gas. Third problem is erosion. Metal loss due to impact of hard particles on the tube surface. Mostly biomass, there cannot be any erosion. They are soft fuels. There cannot be any erosion. Only you will be having deposition and corrosion. Again, deposition corrosion, there may not be much slagging type of deposition in biomass. You have fouling type of deposition and corrosion. These are the two issues concerned with the biomass. So these are all empirical ratio, conventional ratio to assess the slagging behavior of our coal. Silica ratio, base to acid ratio, or slag. These are different conventional ratio available for assessing slagging for coal. So based on the ratio, if iron oxide is 3 to 8, we call the non-slagging, 8 to 15 medium slagging, 15 to so based on all are decided for coal, not for biomass. So traditional slagging indices are based either on the results of the ash fusion test or chemical composition of the coal ash. The application of coal ash slagging indices to biomass ash which are chemically very different, can be problematic. And great care should be applied when interpreting conventional slagging index values for biomass. With caution. When considering potential slagging behavior of mixed ashes, suppose you are planning for co-firing, like the government of India has told the 11 power plants, you go for co-firing, 5 to 10% biomass along with coal. So when considering potential slagging behavior of mixed ashes from the processing of biomass with coal, it is clear that apart from silica, all the significant component of biomasses and principally alkali and alkaline materials are formed fluxes. For example, if you see coal ash, chemical composition, coal is a majority 61% silica, 25% alumina. So almost 90% is silica and alumina. Other things are very negligible. Whereas if you are going for co-firing with biomass, so biomass having lot of sodium, potassium. These are all as a fluxing agent. Here only the problem occurs. See, these are all very refractory material, alumina, silica, nothing will happen. Whereas when you are co-firing with biomass, these are all fluxing agent. These will bring down the melting temperature of the coal ash. Since you are adding some fluxing agent in the form of biomass. So co-processing of biomass with coal will result in a reduction in fusion temperature of the blend and hence increase in slagging potential. So that is why the restriction, they are saying 5 to 10%. Don't go beyond that. If you go beyond that, you will end up with problem. Because biomass, we go, all are fluxing agent, sodium, potassium. It will bring down the coal ash melting temperature lower side. So for the co-processing of biomass at relatively low levels, mixture is still predominantly alumina silicate. So cautiously you can with some hardware you can use the flagging prediction method for coal. In the case of fouling indices, again this is available for coal, sodium, if it is non-fouling, moderate if it is less than 2.5% moderately fouling, 2.5 to 5% sodium is severely fouling, calcium. The fouling indexes for coal ashes are based on sodium content of the fuel because sodium is most available. Whereas in biomass, potentially potassium is available. For most of biomass material, potassium tends to be the dominant alkali metal and is generally available released by, again it's also partly volatile also. So fouling indexes of biomass materials therefore to be based on total alkali, don't go for such classification. Instead, you go for totally alkali content of the fuel. These are all the classification. Fouling probable, fouling virtue based on alkali index. So slagging, fouling are problems that occur when the biomass begins to melt, causing deposit inside the combustion equipment, mostly in superheated section. Most of the superheated section only affected go for rapid burn. See, for example, high mineral content of the grasses in the field cap can contribute fouling and clinkering, potentially expensive problem in the combustion system. Dirt in the field also adds to the mineral content and associated clinkering and fouling problems. Therefore, fuels should be kept free of soil and other contaminants. Biomass inorganic constituents that are volatile in combustion temperature, mostly alkali metal, sodium, potassium compound. Phosphorus complex can be released to the combustion gas in the form of uncondensable vapor. It's going as a vapor. Then something goes as also going as a aerosols. For example, calcium compound goes as aerosol. Rest of the things goes large ash particles. These are the three types of combustor. We have grade boiler, fluid boiler, pulverized fuel combustion boiler. Now we're looking at the corrosion aspect, boiler action. Probably few states will complete it. The biomass materials, industrial other following key chemical characteristics which have been influenced on the high temperature corrosion process. Biomasses tend to be relatively rich in alkali metals, particularly potassium compounds. Then they have the low sulfur, then significant amount of chlorine. So potassium and chlorine plays vital role in high temperature corrosion. Significant corrosion of conventional superintermediate have occurred when the firing most biomass built in metal temperature excess of 450 needed. So these are severe corrosion associated with biomass ash deposit containing alkali metal chloride. So if you have potassium and chlorine, potassium chloride, you have significant amount of superheated corrosion. The reason being, see, potassium chloride melting temperature is 772. But if you see the potassium chloride eutectic, 202. Potassium chloride, iron chloride, eutectic mixture have very low melting temperature. See, potassium chloride, iron chloride, ferrous chloride have very low. Only sodium chloride. So individually, potassium chloride melting temperature is 772, but in the form of mixture, eutectic, very low melting temperature. So pictures are deposit covered in superheated coil, 330 megawatt star-fired boiler. Superheated deposit, then 33 megawatt star-fired boiler. It's a 100 megawatt star-fired boiler, you have the superheated deposit. This is SCM picture of the 33 megawatt super star-fired boiler, SCM picture. You can see here potassium chloride, potassium sulfate. See the chemical analysis of the straw and deposit sample. Straw, you have seen that there are potassium and chlorine. See in the deposit also, lot of potassium. Here are deposits, superheated deposit. You have lot of potassium. So this I think mostly potassium and chlorine responsible for high temperature correction in the superheated deposit. So already I have covered the characterization techniques of everything with respect to corrosion. With this, I am.
Sir, thank you so much for sharing information on characterization of biomasses and the current scenario of fuels and biomass in India. Thank you very much, sir.
Okay, sir.